All right, so there's one final topic to cover in week 9, and that is the last section, normal approximation to the binomial. So this will be one question on the exam. It will say use the normal approximation to the binomial, so there won't be much of a mystery about it. And this all comes down to this idea that we saw in the binomial section of part 5. So when we talked about our binomial, and you can see it on the formula sheet as well, the mean for a binomial was n times p, and the standard deviation for a binomial was the square root of npq. And it turns out that as long as we take a large enough sample from the binomial, we start seeing a normal distribution arise. So I'm going to pull up StatCrunch and show you guys exactly how this looks. So our binomial is basically like simulating a coin flip, right? That would be a binomial experiment. So if we have a coin flip, and let's say we're going to flip 10 coins, we can go ahead and make a histogram for what this looks like, right? It's more of a bar chart because there are spaces. But you can see what happens is the most likely outcome is going to be 5, 50% of 10, right? N times P. And that's going to be true even if we change this up. We could change this to 20 coins. Oops. And now we'd expect to see the most common thing to be 10 coins, and then we'll still see that sort of symmetric tailing off to either side because 10 is the most likely, and then around 10, we're going to get less and less likely. Oh my God, cat, stop trying to walk on my computer. So you can see that. Now, we do need to have a large enough sample size to start seeing this unimodal bell-shaped distribution, that normal curve that's sort of arising. Why we need a large enough sample size? 2 reasons. One is, oh my God, cat, leave me alone. When we go back to just having 10 coins here, while a bell curve sort of fits this data, we're seeing big gaps, right? Remember, the normal distribution is continuous. So 5.5 exists and 5.6 exists. And here we only have these discrete set of outcomes, and there are not very many of them. Whereas if we change this and say maybe make it 100, now we have a lot more outcomes. You can see there are a lot more possibilities. So we're starting to get closer to our continuous variable. We're never going to be right there, which is why we call this an approximation. The other issue with our sample size, besides having all those different possibilities, is that if we choose something that's really unlikely, so let's say we still have 100, so there's a lot of possibilities from 0 up to 100, right? But if our probability of heads is really low, what's going to happen now is that we expected 1% of 100. So we expected to get out 1. So if we make our distribution, now even though there's all these possibilities from 0 up to 100, 1 is the most likely thing, but somehow 0 is coming out more popular than 1. And the reasoning here is that we're not going to get both sides of that distribution. We're not going to be able to go, right, if 1 is the most likely thing, the next most likely is 2 and 0, but we can't keep going to the left and right. So that's where the feeling of the notes comes in right here. This rule of thumb, sufficiently large by our rule of thumb. This rule of thumb is basically saying our expected number of successes and failures is at least 10. So this is the expected, I can't write when my screen is up. This is the expected number of successes. So in that last example, our expected number was only a 1. So that's why we were getting caught up right against this endpoint, and we weren't being able to see both sides of our distribution. So that's expected number of successes versus our expected number of failures. Those both need to be greater than or equal to 10 so that we are far enough away from the endpoints that we can get the entire tail that we need for our normal distribution. And then also 10 so that we can make sure we have enough values that approximation is reasonable. So if this is true, if we have a binomial experiment and we fit that rule of thumb, then we can find probabilities using the normal distribution. And we're going to use that mean and standard deviation to calculate. So let's just go ahead and do one exercise together. I'll go ahead and start a new video for that.